Welcome to a read-along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is section 2.3 on proof. In this section, we discuss three basic kinds of proof, a little bit about how to write proofs, and some background and history. We also discuss, at the beginning, some symbols. This upside down A symbol, which we could read as for all, this backwards E symbol, which you can read as exists or there exists. So let's get started. Let's look at these symbols. The first symbol we're going to consider is this backwards E symbol, exists. Now, it comes down to thinking about the operation of or between expressions. All right. So what is, or union even? Well, what does this mean? This means that at least one of these guys is true. That's what this means. This statement right here means this or this or this or this means at least one of these is true. So we could say even there exists one of these guys, A1 through A4, that is true. That's essentially what we're saying. There exists one of these that is true. We could represent this sequence of saying this or this or this. We could use this notation if we wanted to. We could like kind of index all these guys, this A1 through A4 with an AK, and go from K1 to 4. This is a lot like the sigma notation, except, sigma is kind of funny because we use it for a binary operation like this. If we have a string of things, if we index it and we want to talk about it, we use this other symbol. Here, it's a little more straightforward. We're using the same symbol right here as here. So technically speaking, we could, we could use a plus sign instead of sigma notation, but we don't. Okay, so but anyhow, so what does this mean? Literally, we could read this and say, there exists one of the AK 1 through 4 that is true. That's essentially what we're saying. Or if we're thinking about unions, we're saying that at least one of them contains maybe like the true atom or an element that represents the what's true. So since it contains that, then it would be true. So there exists the truth in there. There exists one thing, at least one of these guys has to be true. Okay, so what if sometimes our indexing set is rather large and sometimes we don't want to write this down. So instead of writing something like this, we write, oftentimes we write this symbol, there exists. In fact, we could say there exists K in 1 through 4 such that AK is true. In fact, this statement right here is the exact same as this one, exact same. And if we choose an indexing set like 1, 2, 3, 4, we could even write this. There exists K in the indexing set such that one of them is true. And so that's basically what this notation means. You could even, especially if like your indexing set is the natural numbers, counting numbers, you could even say this, there exists K in the natural numbers such that one of the AK is true. We could write this, which is the same thing as writing this. So indexing set using a big or symbol. So basically this is just, exists just means having a lot of ors put together, and the number of ors could be quite large, or we could even infinite. You could do this as well. There's various notations, but this essentially this is what this means, and this is kind of how we can think about it. We can just think about we're oring together a lot of things, or unioning them on, or joining them, if you will. Okay, so the analogous idea to do for anding things together is this symbol, upside down A, which is read for all. So, for instance, you could say for all K in an indexing set, AK is true. Because isn't that what this means? If we put ands and everything, that means all of these are true at the same time. Not there exists one that's true, but that all of them are true. So there's various notations that we can use, which are analogous to what we had before. For exists, So that's essentially what this means. So for all k in an indexing set, all of these guys are true. So this is sometimes these notations are useful in writing proofs and in thinking about proving things. Okay, so let's go forward and go to the next subsection. What is a proof? Okay, proofs can be thought of as logical arguments, all right? But we're going to look at this in terms of power set structure with arrows between things, meaning subsets of. So one thing implies something else. So kind of the idea is that we're trying to look at the power set of the different propositions or statements, whatever that we're working with. And we try to discover enough of this power set, enough arrows, so that we can actually force or see how proposition we want to be true is forced to be merged to true, because maybe there's equivalences one way or another, and you're respecting poset structure or whatever else. Basically, proof is just seeing or visualizing enough of the power set to force something to true. So kind of what we need is we need to be able to discover what those arrows are and where those arrows are. And the way we do that is by being able to prove little statements like, if this is true, then that is true. So we start with kind of, okay, if this is like a mathematical type of idea or whatever, we want to show that this will imply something else. How do we do it? Well, we have to go back to what our assumptions are. Our assumptions are the things that we assume to be true. And see this for all, that means all the assumptions are true. So what we do is we assume all the assumptions are true. And if we assume all the assumptions are true and this expression statement, so are these assumptions enough with this to actually make this implication? Meaning, like, if you think about subsets, like the subset of this and this, is that contained in F, if you will, something like that. So it's kind of how we're going to do that. How do we make this implication arrow? Well, here's an example. Okay, so we're going to use an assumption that equality is preserved when both sides of an equation are multiplied by the same constant. So suppose we have this, we have an expression here, or a statement here, a statement E. This is an equation, but a statement E. And let's add to that the assumption, or all the assumptions. And one of those assumptions is that equations will stay the same if we multiply something, something to both sides. So the same thing to both sides. So based upon that assumption with this equation, using that together, we can apply that rule to this, and we end up getting something, and what we end up getting is this. So this is a natural outcome. So basically, whenever we make arrows, we're just using rules. Use a rule on something that you know to be true on something that that you're assuming, and then you get something else. You have just made an arrow. You do this all the time. You've been doing this for years. Whenever you write out something mathematically, solve an equation or anything else, you're actually, in some sense, writing down a system of a list of implications and implication arrows. Like, this implies this, implies this. So if A is equal to B, then that implies that 3 times A is equal to 3 times B. We just made an implication arrow. So making implication arrows are discovering parts of a power set structure. And so using that, we can force truth out of things. And then there's different ways of doing that, and we'll be discussing that in this section. And just be discussing that in the section. So we'll save that for another video here. Thank you for watching.